is Janet and Rabia.
Welcome to Everest Physics Academy.
Before we start, we'd like to recommend our Everest Physics books for high school,
where you can find more explanations and solve applications and problems.
In this solved exercise, we are going to give the expression of the mechanical energy of the physical pendulum-Earth system. Determine the differential equation that governs the motion of the undamped physical pendulum. Determine the expression of the natural period T1 of the physical pendulum. Give the expression of the mechanical energy of the system disc-wires Earth. Determine the expression of the natural period T2 of the pendulum disc-wires. Calculate the values of the distance A between O and G and the moment of inertia I of the disk about the axis delta.
Consider a pierced disk of mass 59 grams that may rotate without friction about a horizontal axis delta perpendicular to its plane through O. O is the center of the uniform disk before being pierced. The moment of inertia of D about delta is I. The center of mass G of the pierced disk D is at a distance A from O, where A equal OG. The horizontal plane passing through O is taken as a reference level for gravitational potential energy. For small angles in radians, sine theta is approximately theta, and cosine theta is approximately 1 minus theta squared over 2. Take G equal 10 meter per second squared and pi squared equal 10. Number 1. Physical or compound pendulum. We shift the disk by small angle theta m from its stable equilibrium position and then we release it from rest at time 0. The pendulum oscillates without friction with a natural period t1. 1. Write down at the instant t the expression of the kinetic energy of the pendulum in terms of I and theta prime. The kinetic energy is given by 1/2 I theta prime squared.
Let's move to part 2. Show that the expression of the gravitational potential energy of the system pendulum Earth is minus mga cosine theta. Consider this figure. We replaced the figure of the oscillating disk in the previous slide by this figure. This figure includes the center O of the unpierced disk, the center of mass of the pierced disk in a certain position during the oscillation. In this position, OG makes an angle theta with the vertical. This figure includes also the lowest position of G, or the position of G at the stable equilibrium position. Now let's move to the expression of the gravitational potential energy. GPE, or the potential energy, is equal to mgzg. Now we want to determine the expression of zg. Here is zg. It is the altitude of G relative to the reference level. Zg is equal to minus OH because G is below the reference level. Now how can we calculate OH? Consider the right-angled triangle OGH. Cosine theta is equal to the adjacent OH divided by the hypotenuse OG. Then OH is equal to small a multiplied by cosine theta. Therefore, Zg is equal to minus a cosine theta. Now, replace Zg in the expression of the potential energy by minus a cosine theta. This is going to be minus mga cosine theta. Let's move to part 3. Write down the expression of the mechanical energy of the system pendulum Earth in terms of mga theta theta prime and I. The mechanical energy is equal to the kinetic energy plus the potential energy. The expression of the kinetic energy is found in the previous slide. It is 1/2 I theta prime squared. And the expression of the potential energy is found in this slide, and it is minus mga cosine theta.
Part 4. Determine the differential equation that governs the variation of theta. Since friction is neglected, or the sum of the works done by the non-conservative forces is 0, then the mechanical energy is conserved, or ME is constant. Using the expression of the mechanical energy proved in the previous slide, so let's differentiate both sides with respect to time. Since ME is constant, then ME prime is equal to 0. 1/2 is constant and theta prime squared is variable. So the derivative of this term is the constant 1/2 times I times the derivative of theta prime squared, and the derivative of theta prime squared is equal to 2 theta prime theta double prime. Similarly, minus MGA is constant and cosine theta is variable. The derivative of this term is equal to the constant minus MGA times the derivative of cosine theta, and the derivative of cosine theta is equal to minus theta prime sine theta. 1/2 times 2 becomes 1, so we have this new equation. Now, since the pendulum oscillates with a small angle, then sine theta is approximately theta. So this sine theta can be replaced by theta. We get this new equation. Now take theta prime as a common factor. In this equation, we have two solutions. The first solution is theta prime equal to 0. But physically, theta prime is equal to 0 is rejected, because if theta prime is equal to 0 as a solution, we have no motion. So the acceptable solution is I theta double prime plus MGA theta equal to 0. Now, divide by I both sides, so theta double prime plus MGA over I times theta is equal to 0. This is the differential equation that governs the variation of theta.
Let's move to part 5. Deduce that the expression of the natural or proper period T1 is given by 2 pi times the square root of I over MGA. This is our differential equation. This differential equation is of the form theta double prime plus omega 0 squared theta is equal to 0. Now compare these two equations, the differential equation and its form. By comparison, you will find that omega 0 squared is equal to MGA over I. Take the square root of both sides of this equation. Then omega 0 is equal to the square root of MGA over I. We know that the natural period is equal to 2 pi over omega 0. Then replace omega 0 in this expression by the square root of MGA over I. This is going to be T1 is equal to 2 pi times the square root of I over MGA.
Focus, please. This is important.
2. Disk D is now welded from O to two identical and horizontal wires OA and OB. The ends A and B are fixed. The torsion constant of each of the wires is equal to 2.8 times 10 to the power minus 3 newtons meters per radians. Starting from its stable equilibrium position, we turn D by a small angle theta m about AB. The two wires are twisted in the same direction by the same angle theta m. D is released from rest at time 0 and start to oscillate with a natural period T2 about the horizontal axis AB. 1a. Write down at an instant t the expression of the torsion potential energy of the wires in terms of C and theta. Since we have two torsion wires, so the torsion potential energy of this system is equal to the torsion potential energy of the first wire plus that of the second wire, and the torsion potential energy is given by 1/2 C theta squared. So the total torsion potential energy of the system is equal to C times theta squared. 1b. Give the expression of the potential energy of the oscillating system Earth in terms of C, theta, m, g, and a. The potential energy is equal to the torsion potential energy plus the gravitational potential energy. The torsion potential energy is just proved is equal to C theta squared, and the gravitational potential energy proved before is equal to minus mga cosine theta. 1c. Deduce the expression of the mechanical energy of the oscillating system Earth. The mechanical energy is given by the potential energy plus the kinetic energy, and the potential energy is equal to the torsion potential energy plus the gravitational potential energy. Now replace the kinetic energy by 1/2 I theta prime squared, the torsion potential energy by C theta squared, and the gravitational potential energy by minus mga cosine theta.
Let's move to part 2. Determine the expression of the natural period T2 in terms of I, M, A, G, and C. This is the expression of the mechanical energy found in the previous slide. The oscillator oscillates without friction, then the time derivative of ME is equal to 0. Now we need to differentiate this equation with respect to time. Let's start with 1/2 I theta prime squared. 1/2 I is constant. Theta prime squared is the variable. The derivative of theta prime squared with respect to time is equal to 2 theta prime theta double prime. Similarly, C is constant, theta squared is variable. The derivative of theta squared with respect to time is 2 theta theta prime minus mga is constant. The derivative of cosine theta with respect to time is minus theta prime sine theta. This is going to be I theta prime theta double prime plus 2c theta theta prime plus mga theta prime sine theta. Now, the oscillator oscillates with small angles, then we can replace sine theta by theta. Therefore, we get this equation. Take theta prime as a common factor. This equation has two solutions. The first solution is theta prime is equal to 0, but this solution is rejected because if theta prime is equal to 0, then we have no motion, and this is not the case. So we will take the second solution, I theta double prime plus 2c theta plus mga theta is equal to 0. Divide the equation by I. This is going to be theta double prime plus 2c theta over I plus mga theta over I is equal to 0. Take the common denominator of these two fractions. This is going to be theta double prime plus 2c plus mga over I into theta is equal to 0. This is our differential equation.
Since the differential equation has the form of theta double prime plus omega 0 squared theta is equal to 0, as you see by comparing these two equations, omega 0 squared is equal to 2c plus mga over I being a positive constant, then omega 0 is equal to the square root of 2c plus mga over I. But we know that the natural period is given by 2 pi over the natural angular frequency. So T2 can be given by 2 pi the square root of I over 2c plus mga. Part 3. Values of A and I. Given that T1 is equal to 4.77 seconds and T2 is equal to 2.45 seconds, use the results of parts 1 and I in order to deduce the values of I and A. Using the result of part I, T1 is equal to 2 pi the square root of I over mga. Squaring both sides, then T1 squared is equal to 4 pi squared I over mga. Now replace each physical quantity by its value. T1 is equal to 4.77, pi squared is equal to 10, m is equal to 59 grams, which is equal to 0.059 kilogram, and the g is equal to 10. After some calculation, we can write 0.3356 is equal to I over A, which is equation 1.
This is the expression of T2, square both sides. You will get this equation. Again, replace each physical quantity by its value. T2 is given in the previous slide. It is 2.45 seconds. C is equal to 2.8 times 10 to the power minus 3 newtons meters per radian. The mass is 0.059 kilograms. The gravitational acceleration is 10 meters per second squared, and pi squared is replaced by 10. Rearrange, we will get this equation. This is equation 2. In the previous slide, we obtained equation 1. Solving these two equations gives A is equal to 3.4 times 10 to the power minus 3 meters, which is equal to 3.4 millimeters, and I is equal to 1.14 times 10 to the power minus 3 kilograms meters squared.
Thank you for watching. If you like this video,
subscribe to the channel, hit the like button and share.